Hi, welcome to our video on our paper FourierNet, compact mask representation for instance segmentation using differentiable shape decoders. It's a joint work between me, Nuri Benbarka, and Andreas Sell. Our goal is to find a mask representation for segmentation which is compact and informative. There are different ways to represent masks. For example, using grids. You can also represent with polygons. And you can use shape decoding to represent or to decode a mask. In grid representation, we discretize the space into a grid, and each grid cell predicts either the foreground or the background. It's easy to process with neural networks, but it requires high memory and therefore can be a little bit slow. Mask RCNN is a great example for this, which is very famous. In polygon representation, we have points on the boundary of the objects, and each point is connected to two other points, and therefore they make a polygon. We have limited number of points in this case, therefore it's possible that we don't have complex masks, but they also require less memory, which means they can be faster. Two examples in this case is polar mask, which has a polar representation, and ExtremeNet, which uses 4 points to predict each mask. Another way is to decode a mask from a compressed vector. These are normally approximate masks, and they require very low memory. However, they can be not so precise. As you can see, in case of explicit shape encoding, the output is an approximate. Our idea is similar. We want to use Fourier series as a shape decoder. A contour is a periodic signal of 2 pi, and because it is periodic, we can represent them by Fourier series. For example, in this example here, we want to approximate a rectangle, and we have 5 components of Fourier series to do that. And in this case, you can see it can approximate as seen in the image here. If we have enough of these Fourier components, then we can essentially predict any mask which can be more complicated. Our network has an inverse fast Fourier transform which predict the contour points, and it forces the network to learn the coefficients of that particular mask that we are training on. The advantage of our method is that we can use small number of coefficients to predict reasonable masks. Because inverse fast Fourier transform is a linear operation, therefore it's differentiable, and therefore we can train it end to end. And with increasing number of coefficients, we can increase the complexity of the masks. So this is the output of our network when we used varying number of coefficients. This output here shows 2 with 2 coefficients, so these are ellipses. And when we increase the number of coefficients, you can see the masks are more aligned to the ground truth masks and can predict more complicated things. So we did all our experiments on Microsoft Cocoa dataset. In this experiment, we can show that when we increase the number of parameters, our output gets better until we reach the 36 parameters, and then it saturates. And we can achieve a mean average precision of 28 with a ResNet 50 backbone. We also compared it with other state-of-the-art methods, for example, with polar mask, ExtremeNet, and explicit shape encoding. And our output was better when we used a similar backbone. With further experiments, you can also see when we have a same image resolution or input resolution for explicit shape encoding and a similar backbone with same number of parameters, our output is better with 2 points from explicit shape encoding. Also, compared to, for example, ExtremeNet and a similar backbone with same number of parameters 8, our output is more than 4 points better in mean average precision. And with other shape encoders or polygon-based methods, for example, polar mask, our output is still comparable. In summary, FourierNet is a single-stage anger-free method for instance segmentation. We only require a small number of coefficients to produce reasonable masks. It's a linear operation, therefore it's differentiable and we can train it end-to-end. FourierNet also outperformed all methods which uses less than 20 parameters. You can find further details in our paper. Thanks.